Yes, so I'm honored to talk about more the dark side of life, because we are going to talk about post-mortem imaging. And also we will include that for preclinical diffusion MRI. So the question is here, this ex vivo imaging or the ex vivo tissue, can we use that as a reliable model of in vivo? And the reason we are asking that is that you could see here this morning, we can do very fancy non-invasive techniques for diffusion MRI that allow us to look into the brain network that we'll probably see later on, but into microstructural features that from DTI or even more complex axon diameters. The thing is that these more advanced models, we want to know something about the ground truths. And it would be nice if we can use the post-mortem here, if the post-mortem here is high quality, because then we can start to link it to more the invasive techniques with electronic microscopy. We can use myelin stainings, and we can also use tracers to validate the tracks. Also, it allows us to use our small friends here, our animal models. So what is actually the difference between ex vivo and in vivo? Well, for ex vivo, we have the good thing is there's no motion, there's no pulse artifacts. The scanning time here is in principle unlimited, so we can go to high signal to noise and high image resolution. We can also use the alternative sequences for diffusion MRI, those that do not have these geometrical distortions that we know from EPRI sequences in vivo. We can also go for possible uses, much more powerful preclinical MR scanners, where the hardware is much stronger than on clinical systems. But we also have some challenges. And these challenges is, for example, tissue degeneration. We also have the influences of the fixative, and we have something that we define as short-term instabilities. So the aim of this talk is actually to go through this ex vivo pipeline. There are about 4 stages here, and we start with the in vivo, and then we will go through the fixation. We will look at how you actually can store your tissue for a long time, the fixed tissue, and how you prepare the tissue for scanning so you ensure it to be high quality. And then you also, of course, when you image ex vivo imaging, that you need to adjust your scan parameters to the ex vivo environment. And then in the end, we will look at different examples, and you will hopefully have learned the challenges for ex vivo, but also be experts to do it yourself. But let's start from the beginning. Fixation. But what is actually happening after death? Well, after death, the brain tissue and the cell lane begins a self-degeneration process due to the action of their own autogenous enzymes, a process called autolysis. So what is happening is actually this example. So this is an extreme example of degenerated tissue. So this is an example where we have a monkey brain, where we fixated it, and the fixation actually failed. But we decided to collect the electronic microscopy anyway. So what we can see here is that this tissue environment does not really look something that we would expect. We can still see in white matter that we have the cell membranes, but we can see the myelin layers here is very loosened. This is another monkey brain where the perfusion fixated went well, and we can see in the electronic microscopy here that the laminars of the white matter are tightly around the axons. We can also see the microtubules here, and we can see the mitochondria here. So there's a big difference here. In this case, we have a microstructural environment that might appear normal in a normal structural MRI, but the microstructural features are quite different from what we accept of in vivo. But here, in the case here, we have an environment which is much more like what we'd expect to have in vivo. So this is a good model of in vivo. This is not a good model. So how do we actually stop this autolytic effects? Well, we need to fixate the tissue. And there are actually basically 2 methods doing that. We can have immersion fixation, so we just take out the brain and put it in a can of fixative. Then we let the fixative passively diffuse into the tissue, and with time it will fix the brain. We can also do perfusion fixation, but the perfusion fixation needs is that we need to use a vascular system, and therefore this only works for animal models, because the animal need to be deadly anesthetized, And what we are then doing is we insert into the vascular, into the heart, and then first we flush the whole system, vascular system, with PBS, then following the fixative. And now the fixative is put immediately into the small capillary beds in the whole brain. So this diffusion, the fixative actually start to diffuse, go directly into the whole tissue and ensure a fixation almost before the dead have discovered that is the tissue have discovered that is dead itself. And then afterward we do post fixation. There exist different kind of fixatives. What we use in MRI, we are using the aldehyde. We have formaldehyde and glutaraldehyde, and this is typically in 4 and 10% solutions. So these kind of cross-linkers, and the formaldehyde is a small molecule, so it is fast penetrating into the tissue and therefore often used. But actually, sometimes you can combine the formaldehyde and glutaraldehyde to obtain a specific feature of the fixation process. And that is exactly what you're doing if you want to fixate the tissue for electronic microscopy. So the penetration time, as I said, it is a diffusion. And it's been shown that formaldehyde penetrates the tissue in about 1 millimeter per hour. So you can imagine if you have a big sample here, it takes some time for the fixative to penetrate large samples. Then we have the always ongoing question about shrinkage. But in a sense, when you just fixate your tissue in this setup, and what we are actually scanning, then the shrinkage is about 5%. And actually, what our experience is that sometimes you can even not see any shrinkage in the tissue. So the shrinkage is minimal at that stage. Now, what is actually, how fast are the tissue degenerating? I showed you in the beginning an extreme case, but how does it actually look like? To start this discussion, we need to introduce the post-mortem interval, the PMI, and that is a time after the brain has died. So this is a nice study here by Hoganen and Rota, who looked into the electronic microscopy and studied what is actually going on with the microstructural features at different PMI time points. And they observe with EM that after 6 hours, you actually can see that the microtia start to swollen. And you also see this effect here, that the laminars around the myelin starts to get loosened. After 24 hours death, then you see this gets much more severe, these effects. But what they also demonstrated, that these effects here, shown here, is about for 25 degrees. But if you lower the temperature when you're working with the fixation process, then you will delay the autolytic effects dramatically. And that means that what the autolytic effects that you observe at this time point here is almost not seen if you do all this at low temperatures around 4 degrees. So therefore, when you're fixating process, always keep your sample and the fluid as cold as possible, but without freezing. So this was the small changes. Laminars are loosening, and we see some swelling of mitochondria. Can we actually detect that with diffusion MRI? And this is a small example. So I just drew a ROI in splenum here. This is an in vivo of a monkey, and we get a mean FA of about 8.4. Now we took the brain and perfuse fixated it. That means our post-mortem interval is about 0. And I draw the same ROI. And now actually the FA values is 0.91, so it has increased. But the increasing could actually be explained that the image resolution in the fixed tissue or the post-mortem scan is much higher, so we do not really have partial effects. Now, in another situation, we take another brain, a monkey brain, and now we do the immersion fixation instead. So in this situation, the post-mortem interval is not 0. And if I make a ROI in the same part of the brain and the splenum, then we can actually see that the FA values now has decreased. So this suggests here that now we are decreasing FA values, suggest that we do have some kind of autolytic effects taking place. So we are sensitive to detect these small autolytic effects. And this lower FA also suggests there might be things happening in the tissue, so it's not really a good model of in vivo. You need to be aware of it. And this is also the effect of post-mortem interval has also been shown by others, where they make a study of rat brains. So they look at post-mortem interval 0, and then they went up to 14 days later. And they did different acquisition along the time, and you can see the first eigenvalue here of the tensor at different time points immediately start to decrease, suggesting that the microstructural environment getting more complex. And that could be, for example, the loosening of the myelin laminas in white matter. It can also be seen in tractography. So what they did in post-mortem interval of 0, then they did the tractography from the corpus callosum, and then you can see nice tract streamlines here. And after 14 days, the brain has degenerated so much that you cannot really do a tractography. So this suggests that the post-mortem interval is really important. So therefore, for ex vivo tissue to be a good model of in vivo in terms of the microstructural environment, the post-mortem interval must be as close to 0 as possible. And you could do that, as showed you, with a perfusion fixation. But you also need to be aware of, even that you're doing a perfusion fixation, then it does not mean that, that all problems have solved. One thing is that you need to ensure that the solution of the fixative is strong enough. So this is an example where the rat brains have been perfused with a different solution of formaldehyde, and with about 4% and even a bit about 2%, then you get robust staining. At lower fixative, you can see you start to get hyperintensities in the T2. And that's not because that you start to get more signal. It's simply because you start to get increased space of small water lacunes. And that's simply because the fixative is not strong enough to fix the tissue. And that can also be seen in histology stains, these small water lacunes. So therefore, ensure to have 4% or higher fixative when you do the fixation of your tissue. So now we managed to ensure that our tissue is well fixated. The post-mortem interval has been almost 0, we hope. So now the question is, how do we store the tissue, and for how long time can we actually do that? Well, we did a study about this. So over a 3 years period, we did have 3 pig brains that was perfusion fixated, and we measured at different time points how the diffusivity changes over time. And we can see that the changes in diffusivity, both in gray matter and white matter, there's no significant changes there. And actually the changes within subjects is smaller than across subjects. And what we also see here, this is the first eigenvalue, it is stable over all 3 years, and that indicates that the microstructural environment is stable. Remember before, when we have the autolytic effects going on, there was a strong decrease in the first eigenvalue. So actually, we are scanning on tissue which is about 10 years old. So if you just keep your tissue well stored, then you can scan it for a very long time. When we have our tissue, then always keep it at about in the fridge in about 5 degrees. Then you ensure it to be an optimal environment. Now we know how to store it, and now we get a time point. We are ready to do our scanning of our ex vivo tissue. So we need to prepare it. And then there are some tips and tricks here. The first one is that what we are always fighting in diffusion imaging is to ensure the signal to noise. And there's a thing here by Shepard and colleagues showing that if you wash out the fixative, then you can actually gain signal to noise. So they have a piece of a cortex here, and they have unfixed situation of T1. And if you do different perfuse fixate your tissue with different types of fixatives, and then you wash out the fixative afterward, T1 is not really affected. But this is different for T2. This is unfixed situation, and then you fixated it, and then you see a significant decrease in the T2. And that also means that we lose our signal to noise. But if you wash out the fixative, then you restore more or less your signal and your T2. The reason for this decrease is simply because that the fixative actually go in and bind some of the water molecules, and therefore it's important to wash it out. This is Laprince from ICMM abstract. They did washout of sheep brains, different sheep brains, and measured how the T2 and T1 changes with time. And you can see here, when you wash out the tissue here, then after about 2 weeks, then you have restored your T2, and the same both in gray matter and white matter. And again, they show that the T1 is not really affected it. Now I say washing out. The question is, how do you actually wash out your tissue? Are you going to put it into a washing machine or whatever? No, you simply just take a can, or a big can, and then you just fill it with PBS, and you take the fixed tissue and put it in there and let it be. Put it into the fridge and just wait these 14 days, and then you starting the washing out the washing out effect. So it's pretty simple. There's another trick. You can speed up your acquisition. It has been shown that you can actually put your post-mortem tissue in gadolinium, and gadolinium lowers the T1, but it does not really affect T2. And that has been shown here that with time, after 14 days, T1 for gray matter and white matter actually is decreased, while T1 seems to be unaffected. Now, when we have a lower T1, allow us to have a shorter TR, and thereby we can acquire faster. So it also need to use powerful gradients, but if you use a Preclinical scanner, that's not a problem. Of course, we need to take care about the heating, both in the system, but also in the tissue that are unprotected. It has been shown in the study that there's no really change in the anisotropy when you do the doping, but the diffusivity is really much decreased. And one thing to be aware of is that gadolinium is a big molecule, so that is staying in the extracellular space. So if you're going to do microstructural imaging, where you want to have a compartment measurement between the intercellular and the extracellular space, and you want to know the fractions, then you need to be aware that the gadolinium might influence this balance between fractions when you do this kind of modeling. So, okay, now our tissue, we have applied our tips and tricks. We are going to place our brain into the RF volume coil. And how do we do that to ensure a mechanical stable setup? And I just show how we do it. It's pretty simple. What we actually need to use is a box of Lego. You can take it from your kids, you can take it from the time when you're a child, or you can buy it. And then you can need to have some micropore tape here, which has no elastic effects, and you just need some ticky-tack. Now you take your brain that has been washed out, and you put it in a double-sealed plastic bag, and of course ensure you do not have any air bubbles around it. You make a small construction here that fits into the coil, and then you place your brain upside down on the Lego construction. You take this micropore tape and wrap it very gently around the tissue. It's simply just to ensure it mechanically stable when you're measuring. But please be aware, do not add any forces to the tissue, because then you introduce geometric distortions while you're scanning. Also notice, it's not just for fun that I place the scanner upside down, and it's not the scanner, it's actually the brain. But the trick here is that the fluid will, due to gravity, go down, and to ensure that the fluid will be around all the cortical lobes while I'm scanning, then this will do the trick. Now, to have this construction stable in the RF volume coil, then you take the ticky-tack here, place it on the corners, and then you place your construction inside in the volume coil, and you press, and then you have a very solid mechanical setup for the scanning, and you can actually scan for weeks without any mechanical effects introduced into this, your setup. So that's cool. But one thing is that now we have ensured such a mechanical setup, we need to test it, because we can introduce short-term stabilities and into our acquisition. And short-term stabilities is only something that appears in the first hour of the acquisition. And this is common because when you handle the tissue on the construction and put it into the scanner, then the tissue is a bit soft. So when you handle it and touch it, then you will introduce mechanical forces to it, and it will be like a spring that takes some time to stabilize. And we are measuring things in microstructural length scales, so therefore it's important to ensure that these mechanical instabilities are not introduced in our setup. How to measure it for these examples? Well, what we did here is that we first acquired all even slices, all the diffusion-weighted imaging, first the B0s and then the 61 directions, and then afterward we acquired all the odd slices, and then we concatenated the signal or the data set. If there are any changes between even and odd slices, indicate that during the scanning time of the even and odd slices, there has been introduced mechanical effects, and that should not be the case in a tissue ex vivo setup. And this is an example for 3 brains, shown for 1. So if this is the time when the setup has been prepared, and we start acquiring data immediately after scan time, after half an hour, then we can see we get these stripes introduced into our dataset, suggesting that we have these mechanical instabilities. After 15 hours, then we can see that these stripes disappears, and actually now is the time that we can acquire reliable, high-quality data set without any of these distortions introduced in the dataset. Then one could say, well, that is not only mechanical, it could also be temperature. Well, you can make a ROI in the fluid, and then you can see after a few hours the temperature has been stabilized. So that is not the problem. So there are mechanical stabilities going on, and the thing is they are nonlinear, so you cannot correct them afterward. If you do the setup I showed you before with the Lego, then the mechanical stabilities, you will actually see they are stabilized about 5 hours. But this is a setup that you always need to check yourself when you do ex vivo imaging. And you do not need to do it every time, you just need it to be the first time so you know how it looks like. All right, now we have the brain is in the magnet and everything is stabilized. Now we are ready to do the acquisition. And when we do the acquisition, then of ex vivo, then it has been shown that ex vivo is similar to in vivo, the anisotropy, and that suggests that the microstructural environment is the same. But it's also shown that the diffusivity is decreased about 60 to 80%, and that means that we need to increase the B-value. So for DTI on ex vivo, then normally in human we have a B-value around 1,000. But because that we have decreased diffusivity, then we increase the B-value to about 4,000. And just to show an example here, if you acquire 2 lower B-value, for example 1,000, how it influences the fiber direction reconstructions. So this is in white matter. You can see a B-value of 1,000, then it's hard to see the directionality of the tissue in this region here. But we have it about clear directionality and crossing fibers with a B-value of about 4,000, and you can go very high up to 15,000, and this stays stabilized here. So it's really, when you have ex vivo imaging, you always need to acquire higher B-values. You need to adjust your B-values to this changed diffusivity regime. And remember, temperature control. Measure your temperature during the scanning, because the tissue is not protected like in vivo. So therefore you need to know the temperature around the tissue. And that's simply because when you do very fine experiments, we want to do something that we cannot do in vivo. Then diffusivity is very sensitive to temperature changes. So therefore you also need to ensure that. Okay, what can we use postmortem for? Well, this is an example that this is a typical clinical human dataset from our clinical 2.3 isotropic voxels. You can go higher with a human connectome. But the thing is, if you just take a postmortem here of a monkey brain, then you can see immediately that you can go to very high resolutions and using this setup that I described. You actually can start to see layers in hippocampus, and you can see nice structures in cerebellum, and you can also clearly see that is standard, more or less, that you can see the organization in cortical layers. You can go to very high resolution, but you do not, as you can see here with the diffusion tensor model, gain much more because the gross anatomical structures already are appearing at this image resolution. Of course, the scan time takes a bit longer, but who cares? We have the time, we just want to have high quality and want to prove something that we cannot see in vivo. There's one thing that we need to be aware of. So I know this talk about diffusion, but we also need to have a look at the T1 contrast. So in T1 weighted images in vivo, we know that white matter is white and gray matter is gray. But we have a shift in ex vivo. So here the white matter is gray and the gray matter is white. If we compare it to the diffusion-weighted datasets, the T2s, then we can see that white matter is dark as expected, and gray matter is lighter than also expected. And we can see the quality differences between a typical clinical and a typical post-mortem data set. The reason why I mentioned this gray matter white matter shift is that it has been suggested that you can take a ratio between the T1 and T2 ratio and get an indicator of myelin content, like Glass and Faesen suggested, that you can do in vivo. But because of this shift in intensity, that you cannot do in ex vivo. So, but still, we can do very cool stuff with diffusion MRI. This is just some examples. You can see this is a small piece of human visual cortex where you can see different layers in cortex. And you can also see here, this is the whole brain of a pig brain. You can actually see the orientation here also of the different layers in gray matter in the cortex. And this is the same thing as you see in many other animals. You can also do some of the more extremes. This is by Flint and colleagues. They have managed to look at the single alpha motor neuron, where you can actually see the diffusivity in the extracellular space of the neuron, and that is pretty cool that you cannot do today in vivo. You can also use this for direct validation. So direct, I mean that in the same brain, we inject a tracer, and in the same brain, we acquire the diffusion MRI, and we can do tractography for validation. So this is an in vivo tracer, the manganese, and then we can do the tractography in the ex vivo world and compare the two. You can, of course, also do diffusion MRI on human postmortem that have been immersion fixated. And therefore, it's also a strong indication that there's autolytic effects introduced in these human data sets, in the tissue. And the thing is that you can see here that it looks like that you have nice structures, but still don't be cheated. And this is also a lot of work done by the group in Oxford by Carla, also shown that the FA value are low and they correlate with the postmortem interval. But you can do extract the larger fiber tracts here. So there are something they can do. You just need to be aware of is the microstructural environment might have changed and not is a good model of in vivo. You can do it another way around that we did here. So this is active X axon diameter measurements. We did prove it in a fixed monkey brain, and we compared with the possibilities actually also do the same thing in vivo. And because we have this post-mortem brain and we have the powerful Preclinical scanner, we can also start to look at how important are the hardware to be able to extract these microstructural features. And we have studied in the same session the different gradient strains. But there's also things that are different between in vivo and ex vivo. For example, when we do compartment modeling here in ex vivo, then we observe there's a small compartment of spins of water molecules that are captured during the diffusion time. So they do not move. And this compartment you do not see in vivo. The reason for this could be that fixation, of course, we have stopped all physiological processes of cell membranes, exchange and everything that has stopped in ex vivo. And that could be a contributor to this additional compartment. But it could also be that it's known, it has been shown, that when you have tissue and put it into the formaldehyde, then you actually can see small bleeps appearing in the tissue. If this is the case, what we observe here, we do not know. So in conclusion, ex vivo MRI of brain tissue is challenging. But if you have insight into the key elements of tissue degeneration and into the setup, then it opens a unique translational door into anatomical details that you cannot see in vivo today. But you need to ensure the tissue quality. It needs to be as close as in vivo as possible. And the trick here is to minimize the post-mortem interval. And here you can use perfusion fixation, and that works for animals. And you can also look at immersion fixation, but that should probably be more on smaller samples. And the challenge is to keep a low post-mortem interval in humans. Too weak a fixative is not good. That will also introduce degeneration because it cannot fix the tissue well enough. Then we have the acquisition. So you need to wash out the fixative, the free fixative, and that will restore the T2 and increase signal to noise. You have these short-term instabilities during the first hours in your mechanical setup, and that you just need to verify and avoid including these artifacts into your data set. Then you can do fancy thing with ex vivo, and you can do validation. But first of all, you need to adjust your scanning and parameters to the ex vivo environment because of the lower diffusivity. But then you can also do tractography versus invasive tracers. You can do advanced microstructural imaging and compare it with electronic microscopy or staining or whatever you want to. And you can also introduce and look at new type of diffusion-weighted sequences that cannot be done on clinical scanners today in vivo, but can make a proof of concept in complex, in real tissue environment as ex vivo with this ex vivo setup. So that was the end of the story. And I will just say that we have a lot of our ex vivo dataset that you are free, that you can download. There are some they're both from pig and monkeys, and we also have the microstructural from here, and we have whole brain that you can do tractography, and also have some data sets where we have the manganese tracers, so you can do your validation. So just have fun with the ex vivo. So that was it. Thank you.